Authored by a veteran chemistry teacher, Abdul Shakur, these two textbooks provide all the essentials that would not only enable students to master grade 11 chemistry, but to excel at the next higher level in this subject. What make these texts unique are their creativity and profundity with which concepts are explained for clarity and mastery. The following is one of a set of 44 different tutorials created by the author, using materials primarily from the text Chemistry 11 in Focus. I hope you enjoyed this video. If you liked it, please give it a thumbs up and don't forget to subscribe. We will see you in the next video and thank you for watching.
Our lesson today deals with qualitative analysis of ionic compounds. And it starts on page 114 and it ends on page 118 from the text Chemistry 11 in Focus. It deals today with an introduction to the transition elements, testing for cations, testing for anions, and analysis of ionic compounds. As can be recalled, ionic compounds are composed of metal ions, cations, and non-metal ions, anions. The process by which these ions are identified and separated in ionic compounds is called qualitative analysis. But before we go on to do analysis of compounds, sometimes students want to know why ionic compounds of the transition metals are colored. The following is a brief explanation of how this phenomenon happens using copper-2 ions. You don't have to know this, but for the curious minds, you can read it. So I'm leaving that there for a minute or two for you to read, but there is a figure below that I will use to give a brief explanation of what you're reading there. These involve some very important, intriguing concepts, and I don't expect any student to learn that. But some teachers sometimes do not know how this happened because they've never studied that aspect of chemistry. So that's why I'm leaving that there. I've done this, for everybody to have some degree of understanding as to why transition metal ions have colored compounds. So I'm leaving that for you to read. You can stop the video and read that. Pause the video and read that. I have to go on with my work here now, so I'm going to just push that up a little bit more there, little by little, so you can read with lightning speed, not like me. Briefly, we've already spoken about elements having s orbitals and p orbitals. They also have d orbitals. Only I'm showing you here, I define d orbitals of copper-2 ion. These orbitals, as they are here, are called degenerate orbitals. They have the same energy. So if I have some anhydrous copper-2 sulfate, if you take hydrated copper-2 sulfate and you heat it gently, it'll turn from blue to white because you're pushing off the water molecules there. In that state, these orbitals here are said to be degenerate. If water is added to that, all of a sudden the compound looks blue. The reason for that is because water molecules form what is called an octahedral complex with the copper-2 ions. The water there are called ligands in this arrangement. So when water encounters some of these orbitals there, these ones here are pushed away from these ones here. So that's why we say water molecules cause splitting of these orbitals here. And when this happens, the electrons from the lower set of orbitals here will want to go, one of these will want to go up there to be inserted in that orbital there. But it needs energy. That is why we say that it will absorb red photons from light. And because it is absorbing red, what comes out of the solution now is cyan looking color, but is complementary to red. If we add ammonia to the solution now, what happens, because ammonia is more influential in terms of pushing orbitals away, it will push these up a little bit farther up there, see? So these will go some higher up there. To put an electron from this orbital here into that half-filled orbital there, it requires more energy. And in this case, a yellow photon is used. Remember, yellow is more energetic than red in the visible spectrum. So when yellow photon is used to push that electron up there now, to fill that half, this one is going to be up there, it now releases a blue color, because this now is the complementary color of yellow. And that is why now the color will change from cyan to blue. I hope that was helpful to you. Okay. Now we go on to look at the different colors of some of these transition element ions here. Before you go further, this was the cyan color of the complex, hydrogen complex. Okay. You see it has these water molecules there. When you pour ammonia molecules into that now, it forms this copper ammonium complex here that is deep blue here. Okay. All right, you can do that in school. Just take some ammonia, drop it inside here, and you see you get this beautiful color. So these are some of the colors of a few transition elements there. This colors, this is blue, iron 2 is light green, iron 3 reddish brown, yellowish brown, manganese 2, light pink, Mn7 magenta color, chromium 3 green, chromium 6 orange, vanadium 3 green, vanadium 4 blue, vanadium 5 orange, and nickel green, cobalt pink, titanium purple. And here you're seeing some real solution. This is copper 2 here. This is manganese 7, as in the case of permanganate. And then you have iron 3 solution here and an Fe2 solution. So you can see these nice beautiful colors that you have for transition elements. Analysis of cations. Cations of ionic compounds aqueous solution can be identified in a number of ways. You can inspect it, like you see there just now, by the colors produced when their solutions are heated in a Bunsen flame. A flame test involves taking a sample of an ionic compound and you heat that in a Bunsen flame, and whatever flame is produced, it is characteristic of that particular ion there. So here are some ions, and these are the flames that are produced specifically for each of these ions. You can see potassium here is lilac, sodium is yellow-orange, lithium is carmine red, cesium is violet, calcium is yellow-red, strontium is crimson red, barium is pale green, rubidium is purple, zinc is bluish green, and lead is bluish white. Let us say you have a compound that's lost its label, right? And it belongs to one of these here. All you do is to take a sample of it, do a flame test, and whatever flame you get, you match it with one of these. If you get a crimson red, it means that it is strontium ions that are present there. Some of these ions there can also be tested by chemical means. For example, if I have an iron 2 compound and I add sodium hydroxide to that, a sample of it, okay, you will get a green precipitate here, and that is indicative of the presence of Fe2 ions, okay? Now, if you want to see if Fe3 ions are present, add NaOH again. If you get a reddish brown precipitate here, it is a confirmatory test for Fe3 ions, okay? If you want to see the presence of Cu2 plus ions, add sodium hydroxide again, followed by a solution of ammonia. First of all, when you add the NaOH, you're going to see a nice blue gelatinous precipitate here that redissolves in the ammonia to form that nice blue solution we showed you before. Zinc, we add sodium hydroxide to it, you get a precipitate of zinc hydroxide, whitish precipitate. And if you add excess ammonia to that, or excess sodium hydroxide, it redissolves to form a colorless solution. How do you test for ammonium ions? Let's say you have ammonium chloride. Add some sodium hydroxide to a sample of it. You get the evolution of a pungent smelling gas that turns damp pink litmus paper blue. So that is a test for ammonium ions. Add NaOH to it. If a gas is produced that turns damp pink litmus paper blue, it is indicative of the presence of ammonium ions. And here now we're going to do testing for anions. If you want to test for chloride ions, let's say you have a solution there and you want to know if it is a chloride, you add to a sample of that silver nitrate solution, and when that happens, you get a white precipitate. If this white precipitate redissolves in ammonia solution, then it confirms that chloride ions are present. You do the same thing now for bromide. You add that. In this case, you get a creamy precipitate. And if you want to confirm that it is bromide ions, you try to redissolve it with your dilute ammonia solution. It would not so easily. It readily dissolves in concentrated ammonia solution. So let us say you did a test and you were not certain whether it was chloride or bromide ion. You do that test. You get a precipitate, you're not certain if it is, you're not seeing good like me. You don't know if it's chloride, it's silver chloride or silver bromide. Try to dissolve it in ammonia solution. If it readily redissolves, then it's this. If it doesn't, then you have to pour a large quantity of dilute ammonia, or it redissolves in concentrated ammonia solution. Iodide, you add again silver nitrate solution, you get a yellow precipitate that doesn't redissolve in ammonia solution, and that is confirmatory test for iodide ions. If you want to know if a solution contains carbonate ions, you add dilute HCl, hydrochloric acid, to a sample of the solution, and you will get effervescence. Effervescence, you see fizzing taking place, and a gas is produced. If you pass this gas through lime water and it turns lime water milky, then it confirms that carbon dioxide is produced, and that could only come from carbonate ion with acids. So that's a confirmatory test of carbonate ions, okay? Now, if you want to know if a solution has sulfate ions, add barium chloride to it. And with the solubility chart, when barium combines with sulfate, you get a precipitate, white precipitate. But this white precipitate can be confused with other things. If you try to redissolve that in dilute HCl, it wouldn't, okay? This other guy here can be confused because their ions form a white precipitate with barium chloride. Also, it gives a white precipitate here. If you pour more dilute HCl onto it, okay, it redissolves. So to know the difference between a sulfate and a sulfite, when you get your white precipitate, try to redissolve this white precipitate in dilute HCl. If it doesn't redissolve, then it's sulfate ion. Sulfate is present. If it redissolves, then it's sulfite. But look what happens. When you try to redissolve this with hydrochloric acid, another reaction takes place. See? It produces barium chloride, both of these are soluble, and sulfurous acid. Sulfurous acid, being relatively unstable, breaks apart to give you some sulfur dioxide here. You can smell that. But if you want to confirm that this is sulfur dioxide, pass it through pink permanganate solution and it will go colorless. So that's a test for sulfur dioxide here. And this is how you distinguish between sulfate and sulfites. Nitrate ion, you add sodium hydroxide to a sample of it. And to that, you add pieces of aluminum. If you do that and you get this pungent smelling gas that turns pink litmus paper blue means ammonia gas is coming out there, and that confirms that nitrate ions are present because it's a complex reaction happens there in which you get a complex of aluminum formed there with all these things reacting. It's a very complicated reaction. So that's how you test for these anions. And these are some questions here for you to do. You ought to see which one of these are colored compounds, which are not. You identify the transitional elements there, and these will have colored compounds. Those will be colored. Now you're going to do analysis of a few ionic compounds. All right. Let's suppose that someone says to you, I have a bottle here. I don't know if it is potassium chloride or not. Okay. We want to confirm that. So first thing you will do is what is called a flame test. I explained how you do that already. If a lilac flame is produced, then it indicates that potassium ions are present. You do the test for chloride ions. You add silver nitrate followed by ammonia solution. If the white precipitate that is formed redissolves in ammonia, then it confirms that this guy is present. So your formula is potassium chloride here. If you want to know if a solution contains copper 2 sulfate, take a sample of it, add sodium hydroxide to the sample solution. If you get a blue gelatinous precipitate, then that indicates that copper ions are present. You want to know now if sulfate is there, take a sample of the solution, add barium chloride solution to it, followed by HCl. If a white precipitate is formed that does not redissolve in hydrochloric acid, then that confirms this ion here, and indeed that's a compound. Zinc bromide, you can do zinc 2 times, different ways. You can do a flame test that will give you a bluish green flame, okay? Or you can do the one described, add a sodium hydroxide to that, and then you try to redissolve it in excess NaOH. If it does redissolve, then zinc ions are there, and that's your compound there. You want to check for ammonium carbonate now. Take a sample of a solution, add sodium hydroxide to it. Ammonium ions will give this pungent smelling gas that turns pink litmus paper blue, and it indicates those ions are there. Carbonate, you get effervescence with this guy, and you pass that through lime water, is going to go. The gas that is produced, if it turns lime water milky, it means that carbonate ions are there. That's your compound there. If you want to know something is lithium sulfate, the only thing you can do for lithium is to do a flame test. If you get a carmine red flame, then it indicates that, of course, this guy is there. Sulfite again, add barium chloride to it, followed by HCl, okay? It will redissolve in this one here, white precipitate redissolve, producing this gas here that decolorizes potassium permanganate solution, and that will be your compound here. This is easy here. Same thing here. How would you carry out some tests to show that this guy is barium chloride, or if it is lithium carbonate? Just analyze it the way. You make samples of that. Get a sample, you add the sodium sulfate here. You check in here, you want to know if it is barium chloride. Let's say you're dealing with one if it's barium ions are present. Now you know barium will form a insoluble sulfate, right? So if you want to check out barium ions now, you'll have to add a sulfate to that. So you want to add sodium sulfate to that. If a white precipitate is formed that does not redissolve in HCl, you can conclude that the precipitate was sulfate, barium sulfate, and therefore that will confirm the presence of barium ions. Okay, so this is the reaction here. And then you can do a flame test. If a pale green flame is produced, then it's barium. Okay? And then you want to know what is the ion there. If you want to know if it was chloride, add silver nitrate followed by ammonia. If a white precipitate is formed that readily redissolves inside your ammonia solution, you know it is chloride ions, okay? If those tests come back positive, then your compound is barium chloride solution. If not, then you do these additional tests. Now you want to know You want to identify lithium and carbonate now. If these didn't come back positive, could be lithium carbonate, go through the test for lithium and carbonate ions. You do a flame test or sample the solution. If you get a carmine red flame, then lithium ions are. If not, they're absent. Then you do know your test for carbonate ions. You add dilute HCl. If a gas is produced that turns lime water milky, then you can confirm that carbonate ions are present there, and your compound must have been lithium carbonate. And these are some questions I give students here. Nice questions. Answers are inside the solution manual there. You can pause the video, look at them, you can try to work them out. Or you can buy the manual and get the solutions if you're not clear. All right. This is a question I made up for my grade 9 classes when I used to introduce the scientific method of investigation. I want the kids to do something. Instead of telling them what these steps are, they actually carry out a little experiment here and they come up with their own steps in the scientific method of investigation. So this was it. I give them this. I say chlorine is one of the agents that municipalities use to kill pathogens when purifying water for domestic use. High levels of chlorine in drinking water is associated with risk for bowel cancer. It has been established that people living in two different municipalities, A and B, consume similar types of food and beverages, but they drink water from two different municipal sources. However, people living in locality A experience a much higher incidence of bowel cancer than people living in locality B. The presence of chlorine in water is indicated by the addition of silver nitrate solution to it when a white precipitate of silver chloride is formed. Depending on the amount of chlorine in the water, the higher is the intensity of the whiteness that's produced. Describe how you use a scientific method to investigate this problem. See what I do sometimes. So I get two samples. I say, look, this is from municipality A, that's from municipality B. And I put a little bit of sodium chloride inside the water from sample A. You know what? You got to get a more positive test. Then I'll ask them to go about investigating this problem. They will look at the problem, they'll state the problem, they'll make a hypothesis, right? Then they will have to tell me what materials you'll use, beakers, silver nitrate, whatever they think they have to use. Then they'll give me an overview of what they're going to do. They say get water from locality A and locality B. They test it with silver nitrate solution and see which one gives more precipitate. Then they'll do for me their method, step by step what they do. And then they'll give me the results. Then they analyze the results. And they'll make a concluding statement whether or not their hypothesis was true. And then they'll have to go and further investigate this thing. It could be that it's not the chlorine, but something else. So I hope that was useful to you.